can see me and hear me. We have this hybrid dual setup with people online and people here in the room. So that's good. We'll see how that works. If you cannot hear me or whatever, please feel free to interrupt. And also if there are any questions. So first of all, of course, I would like to thank the organizers for the invitation to speak. As it was said before, so as far as the format, feel free to interrupt at any point. Also, because we have a smaller setting, we can take advantage of that and have a little bit more interaction than we would do if we were a big group. So what I will present is work that I did together with Jeremy Butterfield over a number of years. So part of the work is with him and part by myself. And here is the plan for the lecture. So let me minimize this so that you can see. So you can see the plan. So for lectures, roughly speaking, in the first lecture, we'll talk more about formal matters. We'll approach things from the formal side, which will be today. Then tomorrow I will address more examples. And then in the second part, so on Wednesday and Thursday, I will go into the more philosophical matters, first theoretical roles of dualities, and then practical roles of duality. So this will be part of the schema that I will talk about, which I will first talk about the formal matters, what is a duality in formal terms, and then I will present some examples from physics. Those examples will bring in some of the material that later on I will use for the philosophy. And then during the second part, we will go into more philosophical topics. So the examples that I will discuss tomorrow in particular, they involve particle-soliton dualities in field theory, and also some dualities in string theory, in particular S-duality and T-duality in string theory. So those are slightly more advanced, but I will do that at a level that is feasible for everyone, because it's important to have some knowledge of what is the actual physics of these dualities. On Wednesday we will tackle the more philosophical topics on Wednesday and Thursday. So the theoretical roles of dualities are closely tied to satisfying the schema, so to what is to the definition of a duality, and in particular to the semantic aspects of the schema. While the practical roles of dualities that we will discuss on Thursday, those have more to do with looking beyond the schema itself and looking at further aspects, including epistemic aspects that I will discuss. And also cases of what I will call effective dualities. So cases that are not actually, strictly speaking, dualities, but that are in the neighborhood of dualities, that are closely related. I will say more about this too. So here's the plan for today. I will begin with dualities in physics, simple examples that you are all probably familiar with to some extent. Then I will present the formal schema for dualities. And then I will present my main example for today of bosonization. And I will conclude. So I begin with dualities in physics, in particular, simple examples. Why do we think that dualities are important, and also from a historical perspective, although I won't go explicitly into the history, but what are historically some important dualities that you have probably all seen at some point. And of course, the case of electric-magnetic duality comes to mind, electric-magnetic duality of Maxwell's equations. We have 4 Maxwell equations in vacuum, so with no sources, no matter particles around. And you know that these equations are invariant under this interchange here of the electric field with the magnetic field. If we do this transformation on the 4 equations, then the 4 equations stay invariant. What do we mean by that? Obviously, a single equation is not invariant. What rather happens is that the equations are exchanged pairwise, right? So these two top equations, one is exchanged with the other, and also these two bottom equations, one is exchanged with the other. So that's the sense in which Maxwell's equations are invariant under this transformation here, which we call duality. It's a duality rather than just symmetry, because there is a sense in which these are really two different theories. I mean, the electric field and the magnetic field are really different quantities. And they play different roles in the theory. Certainly, if you extend this theory to more complicated cases. And so this is what we call, this is the basic case of what we call a duality. It's this transformation that is actually an isomorphism of the theory. Another very well-known example is, of course, position versus momentum formulations of quantum mechanics, or the Fourier transformation. We can describe our wave function in terms of just position, or we can describe it in terms of momentum. Actually, there is no actual need to do a Fourier transformation. Strictly speaking, we could just, if we wanted, we could just stick to the position basis and work with that and do all of our calculations with that and do all of quantum mechanics with that. And all of the rules apply in principle. It's just a matter of convenience that for some problems, it's very convenient to go to this, at least at the formal level. It is very convenient to do this Fourier transformation because it simplifies a lot of problems. And of course, conceptually, there is more to be said about that. But at the formal level, at the level of how we formulate, how we set up our theory, this is again duality transformation. It's an isomorphism between two formulations of a given theory. Jeremy Butterfield will discuss this example in more detail on Friday, and I will also say a little bit more about it later. Then another historically important example that you might have come across is what we call Kramers-Vannier duality. It's a duality that was discovered in the early 40s by Kramers and Vannier, which is a duality of two different formulations or two different versions of the Ising model on a two-dimensional square lattice. So we have a square lattice with dots on this lattice and near neighbors interactions that are described by this Hamiltonian here, where at each side of the lattice we have spins Si, and then we have this near neighbor interactions. The strength of the interaction are given by this coupling strength J. We can calculate the partition function of the Ising model as the sum over all the states, the sum over all the configurations, possible configurations of the spins on the lattice, over the product of all the Boltzmann weights. So the Boltzmann weights here are given in the usual way. It's the minus beta times the Hamiltonian, where beta is given. I have redefined beta here to include also J, to include, that's the usual notation, to include the coupling. So beta is here defined as J divided by Boltzmann's constant times T. And so the duality says that the partition function, if you do a transformation on beta that takes this form over here, when a question, when I point on the slides, can you see the cursor? No, but can you see the cursor on the slide? When I point to something, you can see it. Oh, good. Great, thanks. Great, thank you. Because then I know that I can point. So the inversion, so there is a relation between these two couplings, beta and beta tilde. You can solve this equation to get beta tilde in terms of beta. And if you do that, you see that for large beta, beta tilde will be small and the other way around. So it's a kind of strong coupling, weak coupling duality, which I will say more about later, or you can also think of it in terms of high temperature versus low temperature, which is the way that people normally think about this duality. And so if you do that under this transformation of the Hamiltonian, where the Hamiltonian is transformed as a Hamiltonian function of J and also beta to beta tilde, the partition function remains invariant under this overall numerical factor, this overall normalization. So that's the basic form of Cramer's Vannier duality. It was used by Cramer and Vannier to find the value of the critical point. So what they were actually interested in is whether there is a phase transition in the Ising model, and whether they could calculate the value of the temperature for that phase transition. From this model, so the point at which, under some extra assumptions, the point at which beta equals beta tilde, the critical point, is given by this numerical value here. And then later it was used by Onsager to solve, a few years later, to solve the 2D Ising model. Okay, so the 2-point, this can be generalized to encompass not just the partition function, but also other quantities of interest in the theory. Of course, a theory is not defined just by the partition function, but there are other quantities, such as correlation functions of, in this case, spin variables, the spin variables that are sitting on the sides of the lattice. For example, a 2-point correlation function between lattice sides. Now, if you do a duality transformation for that quantity, you will find that it is equivalent, it is equal to the partition function on the dual lattice. I'm sorry that you cannot see probably the bottom of the slide sometimes. That it is with a defect running between the two sides. A defect means that the couplings along the lattices of the sides take various values, take different values. So we are relating a 2-point correlation function on this lattice to a partition function. So no correlation function, but it's a partition function with a topological defect. So rather than calculating something about some property about the spins, we're calculating a partition function where now the lattice itself has changed, namely the couplings. Some of the couplings have been flipped. And this will illustrate later an idea that will come later on in these lectures, in the examples tomorrow, that models that are completely completely local in some sense, local in the sense that we compute a 2-point correlation function, at 2 concrete points, that it is related by duality to some kind of extended object or some kind of topological defect, some kind of topological object, which is this topological defect on the lattice. So that's that's a feature of duality that comes back in many examples. Okay, and then, so that's my third example. And the last example that I want to very briefly flash without going into any kind of detail about it. It's the same example that I had before of Maxwell theory, but now quantum Maxwell theory, in the sense that I calculate the partition function of some kind of Maxwell theory, generalized with an additional term. So here you see f squared is the Faraday tensor squared, so the usual the usual Maxwell action. But now I add an additional term, which is a topological term. It's topological because it's a total derivative, which doesn't change the equations of motion. And now I have two so to speak, two theories here. I have Z1 and Z2 with different gauge fields A and B. So, and I have a duality between them. So I have this small T1 of A and T1 of B. They're dual to each other. What is this duality transformation? Well, it's similar to the usual transformations that we have for Maxwell theory, only that it is now generalized. So the couplings are given basically by these transformations here. They look numerically, the numerics is a bit complicated, but it's quite simple. So the only thing, and you can actually simplify this quite a bit by writing this complex value, this complex coupling tau in terms of the charge, the electric charge, and the theta angle. So theta is the theta angle and E is the electric charge. And then under the duality transformation, tau goes to -1 over tau. So maybe that reminds you a little bit also of the way that the beta was transformed in the ICMOL. So this is also a case of weak coupling duality. When tau is small, tau prime is going to be large. Now this is in what sense this is a duality? Well, in the sense that these models are equivalent, and to prove that, one way to prove that in this case is to go through what I call this parent theory. It's this theory which has two kinds of fields, F and B. B is a one form, it's a gauge field, and F, it's a two form. It's a two form which is not exact, it's just a two form. And this is a quadratic theory, so you can integrate out any of these theories, any of these fields. You can perform the Gaussian integration to reproduce either this one or this one. So depending on which you choose to integrate out, whether you integrate out one of the vectors, sorry, the B or the antisymmetric tensor F, you will get, and you see that in this figure here. So you integrate out B, then you will get the Maxwell theory for the gauge field F. Namely, when you integrate out B, you get enforced the Bianchi identity, so that F now becomes the Faraday tensor. It becomes an exact two form that satisfies the Bianchi identity. On the other hand, if you integrate out B rather than the F, you get this other theory in terms of the other gauge field B. So this is where we integrate out. Now, in this case, it's quite simple, and it's a good illustration of more rich cases where what will happen is that basically this process of integrating out cannot be done exactly. It's not as simple as a Gaussian integral because the theory will be nonlinear. So that happens typically in quantum field theory, like Seiberg-Witten theory. And then the duality between these two theories here will not be an exact duality. But still, it will be something close to the idea of duality. And so you can, and one way to work with that will be to go up to this bigger theory so that you can derive various results. So basically, the duality will be used as a tool to find out various results about this bigger theory that you are interested in this case. So this is kind of a miniature version of that more rich version that physicists are used in other contexts in quantum fields. So these are my four examples. The first three are the very simple ones that illustrate what I will now show as the definition of what a duality is. This fourth example, I will talk about it later when I talk about effective dualities. Although at this level, it is also a case of an exact duality. Okay, so those are my introductory examples. So now we move to the second topic, which is how to formalize this. We see that we have very different examples, very rich examples also, but there is some common structure to all these examples. how can we formalize that structure? And that is what with Butterfield we have called our schema for dualities. The schema, by the way, will not only be formal, we will also add semantic aspects, but I will only do that on Wednesday. So today will be the formal part of the schema. Okay, so before we do that, I want to introduce some of our usage of words, of the words theories and models, which are, of course, two words that are very used, maybe overused in philosophy of science, and so one has to specify what meanings one endorses and which one doesn't. Like I said, today I'm interested in formal aspects, so I will work with bare theories, so theories that are formal, that are not yet interpreted physically. So that's what I call a bare theory. It's basically a calculus that you use for what later on is going to become your physical theory. Now, a bare theory can be realized, or I will say that it can be modeled in various ways, like the different representations of an abstract group of algebra. So if you have an abstract definition of a group or of an algebra, you have a set of axioms that the algebra has to satisfy. Then you look for representations of that algebra, and then you look for models that satisfy those axioms. That is what I will call models. Actually, that is quite a normal use of the word models in philosophy of science, I would say. Now, these models are in general not isomorphic, of course, like the different representations of an algebra do not need to be isomorphic. And they differ in various ways. They will also differ in their specific structure, like different equivalent representations of a group and different inequivalent representations of a group will differ in their specific structure. So even if you have isomorphic models of a group, you might have very different specific structure just because the representations are very different. So you might have one representation in terms of matrices and another representation in terms of some other structure like a vector space or spinors, and you could still have an isomorphism, but the specific structure is very different. So we say when the models are isomorphic, we have a duality. So that I will say more about this later on. What I want to clarify now about our usage of these words is that by our use of model and theory, we reject three meanings that are often used in philosophy or the philosophy of physics for this, and especially for this word model. So we often associate with a model a specific solution. So we often say we have general relativity, and a model of general relativity is a space-time that satisfies the equations of general relativity. So a specific solution. We reject that meaning. So our use of models is not restricted to a single solution. So what we call models can have themselves different solutions. So they are more like what we normally call theories. The second meaning that we reject is this idea that a model could be an approximation to a theory. So we have a theory and we have something like, you know, a simple model, like when we build even an engineering model of how wind circulates in a certain space, we build a specific model which doesn't capture, also we do an approximation. We also reject that meaning of model. And the third meaning we reject is being part of the physical world, because I already said that at least for the purpose of the formal side of the schema, the models will be formal. So we may wish to interpret the models later, but at this stage we are dealing with bare models. So they will not be interpreted. So having a model doesn't mean having an interpretation of a theory in physical terms. So we reject these three connotations. Rather, we speak about models in terms of representations of theories, in terms of instantiations of theory. Okay, so that's about how we use these words. And of course, one important example of dualities, part of their interest, is that dualities are surprising. They most dualities that physicists are interested in have an element of surprise. Of, well, I didn't expect that I would find a duality between these two such different modes. I think already in the icing mode, there is an element of that a theory at very high temperature is related with low temperature, and even if you include these correlation functions, you really get very different theories in terms of these correlation functions, or in terms of these topological defects. But in other cases, like in quantum field theory and in quantum field and in string theory, I would say that surprises even more. And the reason for that surprise is what we call the specific structure. So the more specific structure we have, and the more rich and the more different the specific structure is between the two models, the more surprising it is. And of course, I would say a prime example of that would be ADS-CFT, gauge gravity dualities, where we have a theory, for example, in 5 dimensions that is related to a theory in 4 dimensions, so that even the dimensionality of what we call space-time doesn't really match, and that even the notion of gravity that we have in 5 dimensions, that is not there in 4 dimensions. So that's a very surprising type of duality, I would say, and that's the idea that specific structure that is in this idea of specific structure. I will say that since Jonathan and Dana and Johanna Erdminger will be discussing ADS-CFT at length, I will not go in detail into ADS-CFT, although I will occasionally mention it, but most of my examples will be other examples of dualities. Okay, so that's duality as surprising, one of the main motivations why we think that dualities are interesting objects to study in both physics and in philosophy. Of course, for us as philosophers, part of the motivation comes also from the fact that dualities might bear on our question on our notion of theory, on our notion of models, on our notion of equivalent between theories, which of course is a topic that philosophers have been thinking about for a long time. And we will discuss that in the 3rd lecture, and also Jeremy Butterfield will also talk about that in his lecture. And our schema, even though it is formal, our use of words already hints at how that is going to play out when we discuss issues of theoretical equivalence on Wednesday. So let me now introduce a notation that we use for the language that I used in the first part of the lecture. So we have the following notation for a model M that exhibits how we augment the structure of a theory T with some specific structure that I will call M bar. So this model M has some specific structure M bar, and I will not write M in this way. So this would be the kind of straightforward notation that you might come up with, namely a representation of the theory that uses some specific structure. So we use this specific structure to build a representation of the theory. But rather we will write Tm, M bar to reflect that the specific structure M bar is used to build this model. And we could have different models will have different items. So Tm is the part that represents the theory. We will call that the model root, because it's kind of the root part of a model that will not get mapped by the duality. A more specific notion of a theory, you might want, I mean, there are different ways to present a theory, but one very common and very useful way to present a theory in physics is in terms of a triple of a set of states, a set of quantities, and the dynamics. The set of the dynamics basically takes you in and I'll say more about that later. It sweeps out a trajectory on the space of states, and the quantities usually act on, so are dual to the dual in the mathematical, not the physical sense, to the space of states in the sense that they act on that space of states. So that's a very common notion of a theory, just your states, your quantities, and your dynamics. I will specify that more later. And so in terms of this presentation, then our model becomes now a quadruple, where we have a representation of our set of states, of our set of quantities, and of our dynamics with a specific structure. So now our model root becomes a model triple itself that I will call little m, which is simply the triple of the states, the quantities, and the dynamics in the particular, for the particular model that we are looking. So that's kind of the overall notation that I will use in this lecture to present the idea of duality. And there is here there will be an obvious notion, parallel with the notion of symmetry. That is namely that people usually say a duality is like symmetry, but at the level of the theory. That is, while a symmetry acts on the space of states, it carries a state to another state, a state that is the same or that matches your original state. For example, if you take the hydrogen atom and you have states that are related by rotational symmetry in the sense that they have the same energy levels, there is a degeneracy of the Hamiltonian, then there is a sense in which that rotation brings a state to a state that is similar to your original state. And in other cases, symmetry might, like in the case, for example, of a gauge, symmetry might even preserve more quantities. A duality, in the same way, a duality carries a theory to another theory. So rather than carrying a theory to itself by doing an automorphism on the set of states, it carries your set of states of one theory to the set of states of another theory, and thereby preserves some structure. Now we will endorse this analogy between duality and symmetry. And of course, the interesting questions for both sides, so both for symmetry and for duality, come from what we mean by the word the same, what we mean by matching, for example, matching quantities or matching states. So a symmetry A, which I will write for A for automorphism, carries a state S in A to a state A of S in a different state in the same set of space of states. Then is the question, under what conditions do S and A of S represent the very same physical state of affairs? So this is a question that philosophers have asked, for example, in context of the whole argument in general relativity or in the context of gauge symmetries in gauge theories. Similar issues arise for dualities, and we will address them wisely. Now, the symmetries of a bare theory and the symmetries of a model in general will overlap, because like I said, a model represents a theory, excuse me. So if a theory is defined along with some symmetry, so the set of states, for example, is defined to have a symmetry, to have some structure, then the models will inherit that structure. So there is a match, there is an overlap between the symmetries. But in addition, the models have a specific structure, and that specific structure might itself have some additional symmetries which are not necessarily reflected in the theory. And we will see also examples of that. Actually, one example that in the example we discussed before is that the Maxwell theories had a U1 theory, but this parent theory that was equivalent to them, it had additional symmetries because it had more fields. Okay, we will see other examples of this. Okay, so these symmetries usually preserve the values of the quantities. That's often the case for gate symmetries. So, for example, gate symmetries preserve the quantities, preserve the values of correlation functions of your quantum field theory. And so it is common to require that a symmetry preserves the dynamics, that it takes a sequence of states to the sequence of its image states. So there is a commutation or an equivariance condition. Now, for any theory T and any of its modes, there is also a natural condition for the symmetry T to be realized in the models. So I already said that the model was a representation of a theory, that it represents not only the theory, but also the states, but also the particular symmetries of the theory. And so the requirement that the representation respects the symmetry is that there is a commuting map between, on the one hand, the symmetry map. So here we have the set of states of our theory, and we have the symmetry on the set of states, so the automorphism taking states to states. And on the other hand, we have the representations of the map from the set of states, from the theory to the specific model. Now, if the representation is itself to inherit this symmetry, then it means that the symmetry is somehow has a mirror in the model. And so we will require then the natural condition is that this forms a commuting diagram. So if that the representation will basically respect the symmetry, whether we first carry out the symmetry and then carry out the representation, or we first do the representation of symmetry and then carry out our symmetry transformation, should give us the same result. It should not make any difference. So there is a commuting diagram there. Okay, so this slide is to summarize what I have said so far in this section about what we call bare theories and models, and how that is reflected in our notation. So a bare theory is a triple of states, quantities, and dynamics, S, P, and D. A bare model is a quadruple of model triples, and coming with a specific structure, where this little m is itself the model triple, and also what we call the model root. And then there is this natural analogy of between dualities and symmetries, which we endorsed. And we also saw that there is a natural condition for these two notions to mesh. Are there any questions or comments so far? Yeah. Oh, yeah, you have to take the microphone.
Oh, no.
Oh, not this one. Oh, yeah, it's enough.
But very quick. So the condition that you mentioned before about meshing of the representation relation with the symmetry, That's supposed to be like alternative, that's supposed to be formalized as some kind of function, maybe some kind of category of, we're talking about algebras and representations, also some categories of maybe from algebra in this category of representations, or is that just too abstract compared to what we're dealing with at this point?
Yeah, I mean, at this point, I'm not using the category theory framework. But that is, of course, a very interesting question, and I will say something about it on Thursday, because there are other accounts of not of dualities actually, but of theoretical equivalence. So some philosophers who work on the question of theoretical equivalence, they have come up with category theory frameworks, and then they do talk about this kind of functors between categories and their representation and so on. I will say more about it on Thursday, but at this point I'm just having a very simple-minded set theoretic framework in terms of sets with structures and maps of them to make it easier. Which also in terms of the actual physics that we deal with, I think it's a very good framework.
May I ask some more clarification about the relation between M and signed, because I didn't understand very well which is the function of M as something that represent M signed. Can you say something more?
Yeah. So M is the model as it is given. We encounter some model, for example, let's say the position representation of the wave function. That is big M. While M bar is the specific structure. So the fact that we have this particular representation, so the fact that we have this X, the fact that psi is a function of X, that X is what we call specific structure. So if we had a Hilbert space, a representation which is basis independent, then we just have psi, an abstract wave function on a Hilbert space. So that would be our theory. Once we represent that in a particular model, namely in our position representation, then we add this notion that we have something we call X, we have the position. And so we add this, what we call specific structure. So the role played by this variable X, so X as opposed to P, those are two different types of structures.
Thank you very much.
Okay, so now let me, with this notation, let me now give the notion of duality, which is basically isomorphism of model triples. So how does that look like? So an isomorphism between model triples or model roots. Now recall that if we have two moles represented by different structures, then we call them M1 and M2. Then an isomorphism between them. So that is our notion of duality. Isomorphism between two such model triples. That requires two things. Requires some isomorphism on the states, right? On the set of states. That could be so for quantum theories, that is usually isomorphism of Hilbert spaces. For classical theories, that could be isomorphism of manifolds. What kind of isomorphism will depend on your theory. But in any case, we have this isomorphism between the set of states. But also we have an isomorphism between the sets of quantities. Set of quantities will almost always be algebras for us, especially in quantum theories. And so we have this requirement that the two algebras should be mapped also by some kind of isomorphism. I already mentioned earlier that algebras are often dual to state spaces, although I won't actually use this framework much, but and duals here in the mathematical, not the physical sense. So dual in the sense of maps on states. In that case, the duality on the states induces for you the duality on the quantities. But I will not make use of that additional piece of information. So I just, for generality, we just have this triple, and this triple, if there is an isomorphism, it must satisfy these two conditions. That there are two isomorphisms. What is, so far we have defined a bijection. What also this bijection will of course respect the structures that you have on your set of states and on your algebras. In particular, it will be such that the quantities match. So when you evaluate quantities on states, like here, so we pair, so we have pairs of quantities with particular states. So this is what we call a correlation function of a quantity between an operator between different states. That should give us the same result in the first model or in the second model once we map them by the duality. And also the third item, the dynamics, is equivariant. So that the duality map is equivariant for the two triples dynamics. If there is a dynamics, because in some cases the dynamics might just turn out to be rather trivial, but those are somewhat will be somewhat degenerate cases. In general, if there is a dynamic defined in the usual sense of, for example, a Hamiltonian on the theories, then it will be equivariant for that dynamics. So that's our requirement. Okay, here I just made a distinction between the Schrödinger and the Heisenberg bridge. Skip that. And here I have a few slides, but I will just go quickly through them for, again, the meshing conditions between dualities and symmetries in terms of this kind of language. But it's the same idea as before, that the duality should mesh, should form a commuting diagrams with the theory. So now we have defined specific maps for the set of states and for the set of quantities, and that should form commuting diagrams with the quantities. But I will not go through that, because I want to go to three salient types of dualities. There are different types of dualities. And it's good to distinguish them, even though they all fall under this general formalism. But in our examples, we will see that there are various dualities bring out different interpretative questions with them. One is what people call non-classical duality. So it's something that some physicists define duality in this way. So this is the idea that duality is realized only at the quantum level. So we have two classical theories that are very different, so different that they are not dual in any useful sense at the classical level. So the duality only comes in at the quantum level. So some authors have defined duality to be of this type. You might argue, without going into the examples now, you might argue that in some sense, I mean, that there is a sense in which the duality between ADS CFT in a particular limit, so the duality between, for example, supergravity and a certain limit of Yang-Mills theory, that it is of this type because the classical theories are not dual in any useful sense, while the quantum theories are. Well, this would need more work to develop, but that's kind of the underlying intuition behind this idea. Now, what I want to argue that even though I claim that even those examples fall under our framework for dualities, that this particular definition that some physicists give, that it doesn't capture all the examples. For example, it already doesn't capture Canos-Vannier duality, because Canos-Vannier duality is a duality between purely classical models that you don't want to quantize, or you don't need to quantize. It is just an isomorphism between two dual models. And so the duality is already there at the classical level, and there is no need to quantize the models. So if we say duality is only between models that are classically inequivalent, but quantum mechanically equivalent, then we are excluding many things that physicists call duality. Also, for example, electric magnetic duality, which is also an isomorphism of the classical field. So this first type of duality is an interesting type of duality when it comes to interpretations, but it is not a good starting point for your definition of what we mean by the idea of duality. The second type of duality is what we call self-duality. That is also a special case in which we now have the same triple taken merely at different values of the parameters. So before I said a duality is an isomorphism between different theories, in particular, different sets of states, different sets of quantities. Now, in self-duality, we might take the same set of quantities, but those quantities might depend on some parameter, and that parameter might change. And so physicists often consider that a variation of some parameters will not count as a different theory. Nevertheless, they will call that duality, a case of self-duality. And then the reason for that is that basically it satisfies the same formalism, and the two models are, different enough that they do count as different theories. Like, for example, the icing model at low temperature and at high temperature. The only thing you do is you change a parameter, but so it's the same Hamiltonian with a different value of the numeric parameter. But these we normally count them as different theories. Then the third, so for that, physicists often use the name self-duality. And then the third type is effective duality. And it's an important case. This is the notion of an approximate duality, an approximate instantiation of the idea of duality. So, and I will say more about it later, but basically an effective duality, because it is not an isomorphism, it approximates an isomorphism, but it is not an isomorphism. Therefore, it is not a duality. And physicists, or some physicists, sometimes use the word duality also for this case, but the official term for this is effective duality, to kind of emphasize that, well, it is almost a duality, but it is not quite a duality. Okay, so given these types of dualities, there are also some features and roles that come with various dualities, especially when we talk about interpretations of dualities. So far I have talked mostly formally, but to kind of anticipate the examples that I will show tomorrow, where these features will be illustrated, and we will discuss them further on Wednesday and Thursday. 4 kinds of features that I would say make dualities salient and an interesting topic of not only physical, but also philosophical analysis that gives you a rich type of range of interpretations. One is what physicists, what we call hard versus easy. So it's the idea that a hard problem gets mapped by duality to an easy problem. This is purely, a pragmatic question. It's how hard is it to do a particular calculation in a certain basis or in a certain formulation of your theory. So if you find a clever reformulation of your theory to another dual theory, then you might do that calculation that was in the dual theory and then transform it. The second, and this is often, of course, in the idea of weak versus strong coupling. We will encounter that tomorrow. So that there's this sense that if you have a theory defined at a weak coupling constant, that is much easier to deal with because you can do perturbation theory, you can do Feynman diagrams, and so on, rather than a theory that is strongly coupled, where you have to include non-perturbative effects, where you have to do a lot of hard work to get your results. So if you can find a duality that relates those things, then you can see that could be very useful. Then the second element is micro versus macro, or the different facets of this, also elementary versus composite, or fundamental versus emergent, which is that duality often exchange not just theories, but also particular solutions of theories, or of models, I should say. And by doing that, they often exchange what we call an elementary solution with a solitonic solution. Tomorrow I will say what I mean by a solitonic solution, but there is this sense that we already saw that in the Ising model, that we had the kind of elementary Ising model. We could define the correlation function between two spins, so that's kind of an elementary calculation in your theory in terms of your elementary fields, while the dual solution is in terms of not something elementary, but something you have to actually change the lattice itself. So you have some kind of topological defect that you need to define, and that will generalize to other cases. So elementary versus solitonic or topological solutions are often exchanged by dualities. Then the third aspect is the aspect of unification, which is, of course, has been very influential, very important in string theory, because people think that when you have a duality between, for example, 2 string theories or 5 string theories and 11-dimensional supergravity, originally they were 5 or 6 different theories, and now all of a sudden we discover that actually there are dualities, there are hidden dualities between them. So if we're able to kind of use those dualities to relate those theories, then we might uncover the kind of structure underlying them, and then that's what I was kind of aiming at with my very simple-minded picture here, this kind of elementary triangle here, kind of, almost a cartoon picture of that. If we have a duality between these 2 theories, well, we might have this kind of bigger theory where the duality kind of becomes explicit, or it becomes maybe not explicit, but in any case more manifest as just the expression of, doing a certain approximation in one sense or in the other sense, or doing a certain kind of mathematical transformation on one model or in the other. So that's the idea of unification. Apparently, different models are unified in a single theory. This is also what underlies our notion of duality as different models that look different. They're actually very different, but they are all represented. They're all representations of the same underlying theory. And then finally, the idea of symmetry breaking, different vacua and phase transitions. We will encounter that. We'll see that sometimes dualities arise, especially of the effective dualities often formed in this case, that when you go from this kind of parent theory to the other theories by, for example, performing the Higgs mechanism on your theory in one way or in some other way. And so you break the symmetry in one way or another. This is also what happens in the Ising mode. You have a ferromagnet at high temperature related to a different ferromagnet at low temperature. The low temperature one has spontaneous magnetization, therefore it has all the spins are aligned in the same direction. So it's what we call a disordered state. sorry, it's a state where the symmetry has been broken because we have chosen a specific, specific polarization, specific direction for the strings. While at high temperatures, we have the spins are randomized, so we have rotational invariance, we have more symmetry. So as we go down in temperature, we break the symmetry spontaneously in some cases at least. Nevertheless, we can have a duality between the two, which is one of the surprising aspects of this Kramer-Vanier duality, that a highly ordered state, highly ordered theory, could be dual to a highly disordered theory. And that, of course, involves a very non-local transformation between the spins. Okay. I don't know how people feel, if they want to have a short break, or people are fine. People saying that we can go on. Okay. Are there any questions from the room or from? See that there is a hand raised. Laura? I cannot hear you.
Yes.
Yeah.
Okay, thanks. No, this is just a clarificatory question. Perhaps I guess that you will be saying a lot more in perhaps starting tomorrow or Wednesday. Just so I'm coming from theoretical physics, so I'm just a basic newcomer to philosophy of physics, and I've seen that there's an emphasis between the ontological versus epistemic commitments of theories. So in this case, a natural, perhaps intuitive reason of what some ontological commitments on a set of theories regarding dualities, that this duality map somehow preserve those structures that basically enjoy ontological commitments on both theories. Is that right? Perhaps it's not robust enough. Perhaps there are counterexamples that I can think of now, but if it's just because the examples that you are saying are, of course, very disparate theories, as you are just saying, between these Ising models and ADS-CFT. So, well, just if you perhaps you will be saying more in the coming lectures, you can skip ahead. So, thanks.
Yeah, thank you for the question. So that's, of course, an important question. I will talk about it on Thursday. And it's also part of the reason I started with the formal framework, because in the formal framework, we're not yet committed to making any ontological commitments. We simply have a formal framework, and we could have different semantics. So depending on which semantics we adopt, we will have an interpretation of our models in one way or another. So this will be what I will say on Thursday, or what I will go more into on Thursday, that basically from a philosophical perspective, you can go two routes. You can go, there is, and that also depends on the type of duality and on your semantics. So some dualities, so most dualities certainly afford a semantics where you say, well, these two theories, I interpret them differently because, for example, say the Ising model, I'm committed to high temperature. That's something different from low temperature. So these two theories, they may be dual formally, but they are really as theories, as interpreted theories, they are really different. So that is something that you can always do for most theories. But I will also say that that we are justified in some cases to also have a semantics where indeed we will interpret, and that's of course what my whole notation also kind of suggests without necessarily requiring it, that the theory that does the representing, that will be the thing that you are committed to. And one example of that could be is the Hilbert space in quantum mechanics, where the Hilbert space kind of represents the, in some sense, the invariant structure, and not just the invariant structure, but things that we consider to be physical, while most people would say that the specific representation in terms of X or P, that is part of how we choose to do our calculations. And now that there would be more, I mean, even in that case, you could take a philosophical, you could take a semantics where that is not the case, where these are different interpretations, but it certainly allows for semantics where you really say, well, no, my Hilbert space, that is the thing that is physical, and the quantities on the Hilbert space and the dynamics, that's what I consider to be physical. And the other things that has to do rather with how I used to represent it. But I will, yeah, we will go into detail into that on Thursday. But thank you for anticipating. Sorry, on Wednesday actually. Thank you for anticipating.
Okay, thank you very much.
Okay, there's another question from Anastasia.
Yeah, I just wanted also to make like kind of clarificatory question. So about you say that you give like a formal framework without those ontological commitments. It seems to me that the idea of being surprising has a little bit of like some kind of more than formal framework behind it. But I guess this is also something that you probably will go on later, but there seems to be like a very non-objective component to duality as surprising. Or like, am I not understanding it correctly? But seems to me that there is more than just formalism, right?
Yeah, thank you. Yeah, so yeah, I already said that the interpretation of the theories plays an important role in surprise. So here I'm just mentioning why dualities are kind of interesting for both physics and for philosophy. But yeah, so that the notion of surprising itself, of course, suggests a subjective element. I won't actually go much into this particular question, except in the examples. But yeah, that's the idea of surprising that. And when it comes down to particular semantics, then the specifics, I would say the surprise is also in terms of the specific structure. So the more specific structure you have, the bigger the surprise from the point of view of the physical model. Okay. So now, yeah. Okay, so now I wanted to let's go on with bosonization, duality between bosons and fermions in 2 dimensions, which is an example where you can basically illustrate the schema in most of its, or I would say all of the aspects that I have discussed so far, the formal aspects. And this example has the merit that it is simple enough that it is just a 2-dimensional example. So it's just a boson, free boson in 2 dimensions, or a free fermion in 2 dimensions. It's quite simple from that perspective. But it is also, it's an intermediate level example. So it's a little bit more sophisticated than just position or momentum or just the other examples that I gave, which are also quite interesting, but this one is slightly richer, and so it illustrates the schema really well, I would say. So let me say what is this bosonic model. So we will have a duality between a bosonic model and a fermionic model. That by itself is already quite surprising, right? You could have models with different spins, because we normally think of spin as spin 0 or spin half as very different properties. So why should that be dual? Okay. So the basic case is the duality between a free massless bosonic scalar field. So really the simplest quantum field theory in 2 dimensions that you could possibly think of. Just a scalar field, and it is massless, and it is free. And then on the other hand, the next best case, so a spin with, a field with particle half that is also free and massless, a complex, Dirac complex Fermion field. And in 2 dimensions, it's often useful to use complex coordinates, x0 plus ix1, so z and z bar. So z bar is the complex conjugate of z, which parameterizes the complex plane. And the reason this is useful is because now the Klein-Gordon equation, so the equation of motion for this scalar field, so I'm now looking at the bosonic field, right, our scalar field. The equation is box phi equals 0 because it's massless. So in these coordinates, it takes this very simple form. And basically in 2 dimensions, you can think of z and z bar on C as 2 independent variables. And the advantage of that is that now our classical solutions, the most general solution of the Klein-Gordon equation now takes this form here. So phi can be expanded in terms of 2 arbitrary functions. Phi of z is little phi is an arbitrary function of z. Phi bar of z bar is another different, in principle, different arbitrary function of phi bar. So that's quite specific to 2 dimensions, right? In for example, 4 dimensions, these functions are normally not arbitrary, but you have some constraint. They basically have to be on the light cone and things like that, and just so you have some kind of light cone condition. Here we have truly arbitrary functions. The only thing is that they have to be holomorphic. So they can only depend on one variable or on the other. Now, this theory has some symmetries at the level of the action. The action has some symmetry, but also the level of the equations of motion. So there are conformal transformations. A conformal group, and Johanna will, I'm sure, will talk about this, is the group of invariances that includes the Poincare group, but also scale transformations, dilatations. Here it will be the 2-dimensional conformal group, and it also includes what we call fine current algebra transformations, which are some transformations that I will show in a minute. So, what is the conformal group? So here, in 2 dimensions, the conformal group is infinite dimensional. In fact, the 2-dimensional conformal group is the diffeomorphism group that we are kind of familiar with from general relativity, where we can do arbitrary diffeomorphisms, so arbitrary transformations between the variables z and z primes with an arbitrary function, but there is one restriction on these diffeomorphisms, that they have to be holomorphic or anti-holomorphic, so they have to respect holomorphy. So we are not allowed to mix z with z bar. So that's the conformal group. Okay. So we have to respect the conformal structure that we have imposed on C. So the complex plane, we have fixed the conformal structure, and the conformal group is the group that preserves that conformal. This group of diffeomorphisms that preserves that conformal. Now, upon quantization, this group will give what we call the Virasoro algebra. I'll say a little bit about that later. And then the second set of symmetries are affine current algebra transformations, which are of this type. These are also transformations that you can do on the action. So normally I can shift my scalar field by a constant, like here. So if I do this transformation where phi0 is a constant, then normally then my action is just invariant under that. In 2 dimensions, that is generalized because we have this kind of holomorphic structure in the action, this separation between z and z bar. the class of transformations that you can do in this phi 0 can now be generalized to, again, some arbitrary holomorphic, anti-holomorphic function. Okay, and that will give rise, when we quantize this, to another. All right, so these are symmetries that you can do on your action. So these are classical symmetries of the action. You can apply Noether's theorem to them, so that you get the conserved currents that are associated with these symmetries. Now we know that the conserved current for the conformal transformations for the diffeomorphisms will be the stress energy tensor. The stress energy tensor in 2 dimensions, it's a massless theory, so it is a traceless stress energy tensor. So basically, it has 2 components of interest in 2 dimensions, just T and T bar. And Noether's theorem gives you that T is given simply by basically the kinetic term of the action. That's your stress energy tensor. The Noether current for the current algebra transformations for these translations here that generalize the translations that you can do on your scalar field, they are these they are these currents over here, so J and J bar. So, and you see that there is a relation between the 2 currents. So the conserved current for the conformal transformations is actually the square of the conserved current for the current algebra transformations. Now, when we go to the quantum theory, if we now want to, it's all classical, if we now want to quantize by canonical quantization, then we want to get an algebra for these fields. We'll need to satisfy an algebra. And in particular, we will have to normal order this kind of products that we have here. So that's so in particular to define T, we'll need to take care of that. But we still can have these relations now as operator equations. And also, it will be useful to write the holomorphic and anti-holomorphic part of the fields as what we call Lorentz series. So arbitrary holomorphic and anti-holomorphic functions in terms of Z and Z bar. So it's kind of a generalization of a Taylor expansion that may now include both positive and negative exponential powers of Z. But the important thing is that it's, of course, a holomorphic expansion. It's actually, technically, it is called what we call meromorphic, because it does have some singularities, but okay, physicists usually talk about holomorphic. Yeah, so it is a holomorphic expansion. And then because these T is basically the square of J, that will also imply that there are some relations between these coefficients, these Ln's, which are kind of your Fourier or your Taylor expansion coefficients in this discrete Lorentz series. So the Ln's will be quadratic in the Jn simply because T is quadratic in J. Now, given this, you now do your canonical quantization program, and then you find that for the coefficients of the algebra, so the Jn's and the Ln's, they satisfy this algebra over here. So there is an algebra for the Ln's, and then the Ln's, which are the coefficients of the stress energy tensor. They are often called the Virasoro generators, because this is what we call the Virasoro algebra, maybe familiar to some from string theory. If not, it doesn't really matter at this point. But there is also an algebra between the J's, of course, which is this simple algebra here. And then there is a consistency condition, because the LMs are defined in terms of the Jn's. They are quadratic in them, so they should satisfy this kind of relation, which comes from the compatibility condition between the two. Okay, so this is our full algebra. When we do our canonical quantization program, this is the algebra that we get for all the fields all the currents in our theory. And this is called an enveloping Virasoro algebra. It is the Virasoro algebra enlarged with these extra fields, these extra generators, and the compatibility condition for them. And that is actually the result, the central result that we need. So that was a technical part that I needed. So at the classical level for our boson. So this is our bosonic theory, the massless field, the solutions, the mode expansions, the symmetries, the currents. Now we have quantized the currents to get an algebra. With that algebra, we get our Hilbert space. The Hilbert space, as usual, will be the space on which the operators act, so on which will be the vector space that forms a representation of our algebra. So together with the normal ordering and the mode expansions, the tensor and this algebra, that contains all of the information about the quantum mode. So the state spaces are now the vector spaces on which this algebra acts, endowed with an appropriate semi-positive norm, and the quantities and the dynamics are constructed from the operators that satisfy the algebra. So if we have our algebra of operators, then we construct the Hilbert space or the state space by looking at the vector space that form various representations of this algebra, in particular representations that have states of semi-positive norm, and that so those are our physical states. So that's in some sense the usual procedure that we do, at least in one of the procedures that we do to quantize our theories. Only in 2 dimensions, it's slightly richer because you have all these symmetries, and the fact that you have all the symmetries means that your algebra is a little bit bigger, but it's what we actually expect from such a field theory. Now let's look at the other side of the duality. So now a completely different model that in principle has nothing to do with the previous. So we just consider a massless Dirac fermion field in 2 dimensions. Now a Dirac fermion field is complex. It's a complex fermion because it's in 2 dimensions. It can be 2 dimensions allows chiral fermions. So that means that you can decompose psi, your Dirac fermion, into a chiral and an anti-chiral part. Chiral means that you can define a gamma 5, or in this case, a gamma 2, and you can and the chirality is then defined as the helicity, under this gamma 5 or gamma 2. So whether the eigenvalues +1 or -1 or 1/2 or -1/2, 1/2 or -1/2. So that's your chirality. So you can decompose spinors in the usual way into chiral spinors, and then the action takes this form over here. So, and it is again written as before, also convenient to write in complex coordinates z and z bar. So now it takes a similar form as before, only it's now, of course, the first order action. First order in the sense that it's one derivative, so psi del bar psi, and then psi tilde del psi tilde with the complex function. So the psi has to do with the chirality. So the tilde on the psi has to do with the chirality, while the bar has to do with the complex conjugation on the space-time. So those are different things. Okay? One is your chirality on the spinors defined by the gamma 2, while the other is just your definition of the complex structure on the space-time. But it so happens that the chiral when you do that decomposition, the chiral part is, you get the D bar. So there will be, when you write down your solution, there will be a correlation between the two. Now, if we look at the symmetries of this theory, it is actually very similar to the previous one. So there are conformal transformations like before, of course, because it's a massless theory in 2 dimensions. Massless theories in 2 dimensions are in general conformally invariant. So here we can do these holomorphic transformations like we did before. So this just has to do with your space-time, not so much with the fields. And then the chiral and anti-chiral transformations, which are, well, transformations of the spinor by e to the I alpha z or e to the I alpha tilde z bar. So these are, again, alpha is a general holomorphic function of z. So that's a holomorphic chiral transformation, because it's a transformation of your chiral field, but it is also a holomorphic transformation, while the other one is anti-holomorphic, because it's a function of z bar, but it's also it's also right chiral, anti-chiral, because it's a transformation of psi bar. So in that sense, holomorphicity and chirality become coupled. The definition of conserved currents and the quantization of this theory when you go to the quantum mole go actually quite similarly to the previous. So again, you can define Noether currents that go with the symmetries. And you also get, of course, a stress energy tensor. But now the stress energy tensor, of course, takes a different form. It's a different field, so it's a different form. And the same for your generator of the holomorphic symmetry J. I have suggestively called J, but of course this J in principle has nothing to do with the previous J, because this one is written just in terms of psi bar psi. So it's a field that is written in terms of fermions. And there are similar expressions for type bar in terms of psi term. Okay, so if you quantize this and write down again the algebra, the canonical algebra that goes with these fields, then the resulting algebra, even though the fields, the underlying fields are different, but the algebra for the currents turns out to be the very same as the bosonic case. It has the same form. It is again the enveloping Virasoro algebra. I forgot to say earlier that, well, the Virasoro algebra has various parameters. It has 2 parameters, c equals 1 and what we call the level k equals 1. So this is a very simple case of the Virasoro algebra. So that's what we get in this case as well. Therefore, also the state space will be the same, since it is constructed as a vector space on the same algebra, with also states of semi-positive norm. So that in principle, if you didn't know anything about bosonization, this would be the smoking gun for bosonization. Hey, we have 2 very different modes, but they share a common structure. So could they be related in some sense? And well, to that, we need to do a little bit more work. Because, okay, the algebras, we have now shown basically that the algebras take the same form. The algebras are isomorphic or are actually bijective, but are they, is there also an isomorphism of the states? Are for example, the correlation functions of the quantities preserved on the states are states mapped to state and so on. Now, to do that, there is a result in conformal field theory that ensures that for you, which is that the irreducible unitary representations of this algebra, which are the physical representations you are interested in, they are irreducible which means they are kind of basically your building blocks of your representations, your basic particle content of the representation in terms of which you can build on all the others. And then they are unitary because, again, you want states that are physical, states of positive norms. Those are technically called the highest weight states, the ones that are annihilated by the highest weight in your algebra. So that those unitary, irreducible unitary representations of this algebra are unique up to unitary equivalence. So there is a state space, a Hilbert space here that is unique up to unitary equivalence. And also there is a corresponding unitary equivalence for the algebra itself. So it's, this equivalence is not just an equivalence of the state space, but there is also corresponding equivalence of the algebra. So the algebras are also mapped into each other by the same map. So basically the duality map of your state space also induces the duality map of your two algebras. So this correspondence between the algebras is the basis for the duality map, is a duality map. It gives you the duality map between the states and the duality map, the isomorphism between the algebras, between the quantities. So how does that look like? This, what physicists sometimes call the dictionary between the two theories, which is the duality map. It's a map that allows you to say, well, if you give me a set of bosons, a bosonic model of your theory, then using this dictionary, we can construct this fermionic model and vice versa. This is what it looks like. The duality map depairs the affine, well, this we have already mentioned, maps the algebra, so the affine current algebra currents and the stress energy tensor. So it relates the currents of the two moles. So I add, to distinguish the two algebras, I add the subscripts B and F for bosonic and fermionic. So we now have two different kinds of currents, right? And the duality maps one to the other. And it also maps the stress energy tensor of one theory to the other. But of course, we have different specific structure. One is a boson, the other is a fermi. So the two sides satisfy the same algebra. The algebra is isomorphic. Okay, and of course, one thing that is maybe expected when you have an isomorphism between bosons and fermions is that the fermions, which have spin 1/2, to make a boson out of two fermions, you should have two fermions. So a boson should not correspond to a single fermion, but it should correspond to a pair of fermions. That's also the idea of Hooper pairs, that you can form a boson by having two electrons together in a pair. That's the underlying idea, physical idea behind this. Okay, so that is not surprising, I would say. Once you think that there might be a duality of this type, then this is the natural, already on kind of dimensional grounds, you might cook up this as almost the only possible things. Also, certainly given the symmetry, that is the only possible thing that you can come up with. What may be more surprising, or at least something that we might not have thought about before, and that in fact historically wasn't really there so far as I know, is that we can go the inverse. We cannot just make a boson out of two fermions, but we can also make a fermion out of, well, what? What do we need to make a fermion out of bosons? Well, that's not very clear, right? How do you make a fermionic field out of fermions? Well, it turns out that you need, in some sense, an infinite number of bosons. Your fermionic operator is an infinite superposition of bosons, what people sometimes call a coherent state. So it's actually the exponential of this boson. And this is something that is really a quantum result. It's not something that we might have come up classically, because it also has to do with the fact that this is a fermion, so an anti-commuting quantity. So the statistics, while the boson itself is a commuting quantity, but once you normal order, it turns out that this superposition has anomalous dimension, which is k squared over 2, and k squared or minus k squared over 2. In this case, k was equal to 1, so the parameter in the affine Virasoro algebra. So that turns out to be 1/2. So that turns out to give you precisely the spin 1/2. So that we have an anomalous dimension. That's a quantum effect. That's not something that we would have come out classically, and that allows you to formulate this duality between the normal ordering of the superposition of this boson, these boson operators, and the fermions, and the same for the psi theory. So that's the dictionary for the bosons and the fermions. Now, once you have this map, you might say, well, initially I might not have thought about these all kinds of operators in my theory, but now that I have them, now that I know how to construct them, I might just as well include this kind of operator in my bosonic theory for my free boson, and that is allowed. In fact, that is actually allowed by the fermions. Okay. So that is the dictionary, so the isomorphism that we have constructed. Now, to show that this is really a duality, we need, there's 3 things. So this is kind of to summarize what I already said. So we need an isomorphism between quantities that we have constructed, in this case from the currents, which satisfy the same algebra. So all of the operators of our theory will be constructed out of those fields, whose algebra we now know. And also the same for the states. They are all the physical states are given by representations of the algebra, so vector spaces that represent the algebra. And the dynamics is given by the usual Hamiltonian evolution. In this case, the Hamiltonian is just the dilatation operator, the P00 component of the stress energy tensor. And that is also mapped by the same duality. So this same, so basically the stress energy tensor that is mapped by the duality is the operator that that does the dilatations on your 2 quantum field theories on the 2 sides, on the boson and on the fermion. And that's your dynamics that leads you through the state, through the set of states. Now, to illustrate, so this illustrates the basic definition of duality, and maybe now you see why I needed an example that is, well, simple enough from the physical standpoint, that is, it is 2-dimensional, it is massless, and it is free, but it is already quite rich, and in some sense, it's slightly advanced from the mathematical perspective, in the sense that there are all these symmetries. So it is that's what I call it an intermediate level example, because it allowed us to illustrate explicitly this idea of having an isomorphism, but also, for example, the preservation of symmetries. So these 2 theories come in with built-in symmetries. These Hamiltonians that or these Lagrangians that we started with, they have symmetries. The conformal group that is the same for the 2 theories, but also there is this affine current symmetry algebra, which is generated by the J currents. It's the same algebra for the 2. Now, the conformal group is the same symmetry group for the 2 moles, because that's just basically the space-time symmetry of any massless, free massless theory quadratic theory that you will write down in 2 dimensions. That's the basic symmetry of that kind of theory. So you could say that's a theory of that's a symmetry of a theory with some restrictions that you built on that background. So that's the same between the two. But the other one doesn't come for free. So the second one, the affine current symmetry algebra, is actually represented quite differently between the two models. It is, remember, it is represented as translations. We saw in the bosonic model, we saw that it was these translations of the field by arbitrary holomorphic functions, right? While on the fermionic field, it was a very different transformation, not as translations, but as these chiral holomorphic chiral transformations of the field size. So a completely different transformation on the fields. So it is not a priori, not at all clear in any sort of way, also not in the classical theory, it is not clear that this should be the same in any way. Yet their corresponding currents, the J currents, satisfy the same algebra. And so these symmetries act in the same way on the states and on the quantities. So these symmetries were used in restricting the class of admissible models and quantities to begin with, because we restricted to the models, to the Hilbert spaces that respect these symmetries, because we impose the algebra. What we now see is that because these were defining symmetries of our models, they now are also symmetries of our theory. So now our theory comes with these two symmetries, but the second symmetry has a different representation in each of the models. And yet, because you have the duality map, you would go through the diagram, you have a commuting diagram of the duality map with the symmetry. So if you would do, if you begin with the bosonic model, you would do a translation by phi, you would do a duality transformation, you would go, so your symmetry translated state would be the same, would be the chiral translated state of your fermionic model. So would be the same as first going to the fermionic model and then doing a chiral symmetry transformation. So the chi that you find in one leg or the alpha that you find on the other leg would be the same, or would be actually related by the duality. So it's a commuting diagram. And so that follows from our construction. So this is something that well, physicists have worked on for many years already. You can generalize this, and this is a very active field of research even now. This is one of the and that is, it has lots of applications also in condensed matter physics nowadays, because you can generalize this also to higher dimensions, to 3 dimensions, to 4 dimensions. One of the first generalizations that people did, which is more phenomenologically interested than the free case, is the Thirring model. Thirring model sine-Gordon duality between a massive fermion with a quartic interaction and the boson field with a potential that is this cosine potential, is why it's called the Gordon duality. So this is one of the first examples of an interacting quantum field theory where you can again do duality exactly. So the generalization involves this parameter beta, which is basically the parameter of your deformation and also, of course, the mass. And so your duality map will include also changing these parameters around. Also, there are generalizations to theories with non-abelian symmetries, so between fermions with non-abelian gauge groups, and what people called Westervino-Witten model. We will not go into those, but there was a lot of interest in that. There is still a lot of interest in that. And like I said, in recent years, especially since 2012, people have been very interested in bosonization in higher dimensional cases because they think that the idea of duality there is this idea of effective duality that I mentioned before, is that you start with a parent theory and then you can flow in the infrared, depending on how you take your parameters, you can flow to one infrared limit or to another, and then you will end up with one bosonic model with another fermionic model, and those two are related by an effective duality, so not quite by an exact duality, but by an effective duality. And you can use that knowledge of this effective duality, this quasi-isomorphism to find and this existence of the parent theory between them, to find all sorts of intuitive results by again doing a weak strong coupling duality. So tomorrow I will say a little bit more about that, but this will not be one of my examples. All right. So this we will do this to conclude, and then we'll see if there are any questions. So at the beginning, in the first part, we have advocated a logically weak notion of duality. By logically weak, I mean in the usual sense that it applies to very many cases, namely isomorphism of model triples, because you can define such a model triple, such an isomorphism for many different types of theories, and that isomorphism respects the structure of the Baire theory on which you have the representation. So this schema for, and there are various, depending on the structure that you define, there are various conditions that the isomorphism is to satisfy, in particular to symmetries, as so the schema for dualities preserves symmetries in an obvious way by means of a commuting diagram, and this is illustrated by bosonization, as I showed, and you can do that in some detail. Some of the other examples and I think it's good that we went through this one example in quite some detail, because tomorrow the examples that I will do tomorrow are more advanced, but I will do them in less detail. So tomorrow will be more of a narrative and less of the actual kind of hardcore mathematics or physics that I showed here. Also because in those advanced models, you cannot always do that explicitly. In some cases you can, but by far not in all of it. So it was good that at least we have seen some examples where you can do this completely, fully explicitly. But then there are, like I said, there are many other examples where you could, in principle, also do it explicitly, but then you have to do a lot more work. But in those other examples, of course, they will be physically richer and also more, for that reason, more interesting. So because they contain some, either they are interesting quantum field theories in 4 dimensions that might tell us something about, for example, one of the prime examples is 4-dimensional n equals 2 super Yang-Mills theory by Seiberg and Witten, which gives a good model of confinement, up to date, to my knowledge, one of the best models of confinement, because it illustrates the idea of, well, confinement, I mean, color confinement of quarks by pair condensation of monopoles. It's an idea that goes back to Host and Mandelstam in the 70s, that they put forward as a mechanism for confinement, and it was realized by Seiberg and Witten in 1994 by means of this effective duality. And so the idea of duality was kind of key in getting to that duality. So there you see how duality is put at the service of a real world problem. And to my knowledge, when it comes to the problem of confinement, which is one of the big outstanding problems in four-dimensional gates theories. The Seiberg-Witten model is still kind of the most explicit non-perturbative result that we have, where you can see the condensation explicitly and using non-perturbative methods, and you can confirm the 't Hooft hypotheses exactly. Of course, it's a supersymmetric model, so it doesn't mean that it's not the real world. So in QCD, monopoles might play a role, but there are also other mechanisms that people have proposed. So there is more work that you need to do there, but at least in this simplified, more symmetric model, you can use duality to do that. And so you also expect that in some sense, duality might also, if monopole condensation plays a role in QCD, as most people expect, then duality would play a role. And then some other examples that I will talk about are the ones that have to do with quantum gravity, where duality really tells you something about the non-perturbative regime of quantum gravity fields. So here are some references that I have used for today. So actually, what I will talk about throughout these days, it will come out next year in a forthcoming book that I'm working on, the philosophy and physics of duality. It will come out 2023 with OUP, also with Jeremy Butterfield. And then a series of papers, I only listed 3 here, about the more philosophical topics that I will, and about the basic schema, formal schema that I talked about today. Kind of the embryonic idea of that is in this space-time and physical equivalence paper. And then with Butterfield, we wrote a longer paper that shows the full schema, also illustrated by bosonization. And then another paper together with Butterfield on the topic of symmetry that I discussed today's